Good morning. I'll probably do an awkward lean into the microphone here. Thank you for everybody coming this morning. My name is Todd Randall. I'm the Dean for the Faculty of Science and Environmental Studies. And I welcome you to this morning's presentation from the Distinguished Researcher Award for 2024, Dr. Andrew J. Dean. And as I say in a few moments, when I first started in the faculty, I learned there were two Andrew Deans, both in the Department of Mathematics. One had to quickly learn who Andrew J. and who our VPRI is, Andrew P. Are, both mathematicians. And I'm going to go off script. And one of the things when Andy coached me on when I became the Dean, he said, you need to learn a little bit about math. Math is a special department within the Faculty of Science. They do things differently. And in reading the abstract for this morning's talk, I learned how little I know about mathematics. And so I do apologize in advance for that, but I look forward to learning with you. So before I begin my formal introduction of Andrew J., I'll just acknowledge that Lakehead University respectfully acknowledges its campuses are located on the traditional lands of Indigenous peoples. Lakehead Thunder Bay is located on the traditional lands of the Fort William First Nation, signatory to the Robinson Treaty of 1850. Lakehead Aurelia is located on the traditional territory of the Anishinaabe. The Anishinaabe include the Ojibwe, Odawa, and Potawatomi nations collectively known as the Three Fires Confederacy. Lakehead University acknowledges the history that many nations hold in the areas around our campuses and is committed to a relationship with First Nations, Métis, and Inuit peoples based on the principles of mutual trust, respect, reciprocity, and collaboration in the spirit of reconciliation. So as I said, I'm honored today to introduce Dr. Andrew J. Dean, a member of our Department of Mathematical Sciences, who was awarded the Distinguished Research Award for NSERC in 2024. So you folks in the room know probably a lot more about Dr. Dean than I do, given that you're some of his students and his colleagues in the department and colleagues around the university. Amongst his many contributions in research, both the scholarly work and the important contributions to student training, I will also note that Andrew is a very gifted educator as well as administrator. No one likes to admit that out loud, but he's a details-oriented person, and I suspect his training in mathematics has made him a valued colleague on as both department chair as well as the many Senate committees that he served on over the years. We still ask him far too many questions about wording on items related to Senate undergraduate scholarship or Senate undergraduate committee, even though he's no longer a member of that group. Andrew studied at Lakehead as an undergraduate. He completed his undergraduate degree in the mid-1990s before he embarked on his graduate training at the University of Toronto for his master's and Ph.D. as part of what I learned to be the Elliott group. After he finished his Ph.D. in 1999, he returned to Lakehead and started his academic career here with us, first as assistant in 1999, and then ultimately promoted to full professor only a decade later. His specific area of research in math is a field called operator algebras. Again, a little over my head. Their use, and again, I see one of my colleagues from the Department of Physics, their use is widespread in the department in mathematics, as well as areas of physics as well. One of his references describes Andrew as being one of the most important and active members of the very successful Canadian school in operator algebras. So I look forward to hearing more about these contributions to the field in today's talk. Amongst his many achievements here at Lakehead University has been a nearly continuous holding of NSERC discovery grants since he started in 1999, since 2001. And obviously his continuing contributions to student training. He actively trains students at the graduate level, even at the PhD level, even though we don't have a PhD program here at Lakehead, he's found a way to make that work, and including the training of senior undergraduate students, either as summer students or as part of their thesis projects. So in consideration of his sustained demonstration of research excellence and achievements, he is highly deserving of this recognition as our 2024 Distinguished Researcher at Lakehead University. Please give a warm welcome to Dr. Dean as he presents the following talk. classical problems in mathematics.
Very nice, told right until almost the last sentence. It's most important word in the whole thing. Classification problems. Not classical. Okay, so first thing I should start off, as I was saying, is what would I mean by classification? If you've seen the titles of my papers, you've seen this over and over again. So a useful analogy, something that I find useful to try to explain this is, suppose you've got a parking lot full of cars and you want to somehow describe them or classify them or distinguish them somehow. You could do this in a few different ways. I mean, one, you could just have a list of all license plate numbers. You've got a label for each and every car in the whole parking lot. Well, then you've got them all named, but the license plate number doesn't actually tell you anything about the car. It's not really very helpful. What you could have instead is a list of, you could have a shelf of owner's manuals for all your cars. So these things just are kind of a description about how the thing is put together. But this, this might not label every single car individually, but it'll tell you the essential things about it and forget the inessential things. If you have a red one and a blue one, it's still got the same manual and it doesn't notice the red or blue, but it tells you exactly what's, when you open the hood, it tells you where everything is inside, how the thing is put together. So the kind of classification that I'll be talking about today is this second kind, where what we do is we have a label that we can attach to something complicated, and hopefully the label ignores things that are irrelevant or unimportant and lets us see the important things. So this idea of attaching a useful label to an object that'll help you see key things about it and simplify questions about it, I think really first came about with something called the fundamental group. So the students who are in real analysis will have seen this before. And this is maybe a good point. I mean, here I have the definition written out. This is maybe a good point to switch to a picture. So. Okay. So now, the idea with the fundamental group is we have something you can think of as a metric space. So you could just think of it as a subset of the plane if you like. Okay, we just have some sort of blob in the plane. Where more interestingly, it could be a surface like a torus. Okay. And what we're going to look at with the fundamental group is loops in the object. We pick a point, and then we consider loops at that point. So on the torus may go around here like this, or it may go all the way around the torus like that. And what we then do with the loops is that we consider two loops to be the same if we can kind of continuously deform one to the other. So if you think of a loop as kind of like a shoestring, if you can kind of rearrange it without going outside of the space, then we think of the two of them as the same. So if we have a loop like this, we can sort of continuously deform it to a different shape. And that kind of gives us an equivalence among them. And then if we've got a couple of loops, we can also go around one loop and then go around the second one. And that still begins and ends at the same place, so it's still a loop, right? So we could say there's alpha and beta. We can go around one and then go around the other. Okay, that actually gives us an operation. And it turns out that this operation is compatible with our deformations, and it gives us we have an operation. So we have a set and an operation. And it turns out that this set with this operation is an example of what's called a group. So those of you who've taken abstract algebra already know that this is what this is. You have gives us a group. Okay, now the structure of the group tells us something about the structure of the space that we started with. Okay, so if we have a solid disk, say, we have our point picked in the middle. Well, if you take any kind of a loop around here within the solid disk, you can deform it to any other sort of loop. There's no holes or anything interesting about the solid disk. So the pi one of the disk is just going to be the trivial, the zero group. If on the other hand, we take a circle, or say an annulus, as long as we've got a hole in the middle, then our loop might go all the way around the hole. And we can't deform that to a single point because we'd have to somehow wrap it around the hole. If you take your shoelace and you wrap it around a telephone pole, you can't pull the shoelace through. Okay, so if we actually look at a circle here, the group that we're going to get out is actually the integers. Okay, so this is for those who've taken the complex analysis class already. The identification is given by the winding number, how many times your loop goes around the center. Okay. So that was the first kind of useful label. That was used to study things. The spaces are kind of wobbly. Groups are nice and concrete. So you could ask questions about these spaces that might be very difficult to visualize or answer, and you could then translate them into questions about groups and group homomorphisms, and the algebra being very concrete, you could hope to answer things. Okay. So just an example of how this particular one was first used. You have here a question that you could ask about a disk. So suppose we have a nice continuous function from the disk to itself. Does there have to be a point that's left fixed by this disk? Well, you can think of some function. Suppose you're just rotating the disk, well, then it'll fix the center point. But this asks a question about any sort of complicated or weird function, and it's really not clear how you could go about doing that. Well, I'll switch back to a picture here to draw this. It's a little easier to see than it is to see it explained in words. Okay, so our question was, we have a map from the disk to the disk, solid disk to solid disk. Well, as we usually like to do in mathematics, we'll say, I want to show something's true, so what I'll do is I'll suppose it's false, and then deduce something absurd from it. So suppose we have, suppose this has no fixed points. Well, if it's got no fixed points, then I can do something like this. Suppose I have some point Z here. Its image will always be someplace else. So I can draw a line from f of Z through Z onto the circle. Call that new point there G of Z. Okay. So what we get is G is mapping our solid disk to our boundary circle. And you'll also notice that if our point was on the circle to start with, then it's actually just fixed. Okay? So I've now got a way of taking the circle and mapping it into the solid disk, just with the identifying it. And then I've got a map going back to the circle. And the interesting thing is that the composition, if I go from both ways, that's the identity. Okay, so if I've got a map with no fixed points, then I can do this. And what happens if I apply the fundamental group? What we get out is this, with the composition being the identity. Now, obviously, you can't have the identity map on the integers factoring through 0, so it doesn't work. And there's the end of our argument, because it means that we must have had a fixed point. If we didn't have a fixed point, we could factor the identity map through 0. Okay, so that's a case there where we can use the labels and the simplification that the labels give to answer questions about the more complicated object. So this was the beginning of a big subject called algebraic topology. There's another little example that I'll just skim through very quickly. Most people in physics will know a bit more about Lie groups. For those who haven't studied them, you can think of these as groups of matrices. A Lie group has associated with it something called a Lie algebra, which is a nice linear algebra object. The Lie group itself is a bit complicated. The Lie algebra just has a few parameters. And the Lie algebras can be studied using something called diagrams, called Dinkin diagrams. And in this way, it was possible to give a classification for a certain large collection of these Lie groups. You could list them all by saying, well, these were the only possibilities for the diagrams. And it got a little bit better than that, not just showing that because these were the only possibilities for the diagrams, those were the only possible Lie groups. When the diagrams were studied, they found a few that they hadn't known about before. And it turned out that they actually did correspond to Lie groups that were unknown up to that point. So finding the labels had actually led to discovering some new examples that weren't known before. So this idea of using labels, beginning with the fundamental group, sort of leads to the idea of what are called categories and functors. So these are things that the math students have kind of started to absorb already, particularly in abstract algebra. Often when we have a structure in mathematics, we don't only have the axioms describing the structure, but we also have with it some natural set of transformations between structures. So for example, if you had the metric spaces, you have continuous maps between metric spaces. If you have vector spaces, you have linear maps between vector spaces. These are maps that preserve the structure. And with groups, we have things called group homomorphisms, ring homomorphisms, manifolds for those who are doing the 4151 class now. These are nice differentiable things. You can think of them as subsets of Rn, and you can talk about differentiable maps between subsets of Rn. So we think of these things as having class of objects, class of transformations that go with them. And what we would like for our labels is actually some kind of transformation between these two things. So with the fundamental group, we had a transformation that kind of took the metric spaces with their continuous maps, and it shuffled it over to groups and group homomorphisms. So this is what we would like from our labels. They would sort of switch between these two kind of things. And these are what are called categories. You have a collection of objects and a collection of maps between them. They have a few properties they have to satisfy, and you have to be able to compose maps and have identity morphisms. And the fundamental group actually gives you a way of kind of translating from one category to another. And the category you're translating to is easier to work with. It's nice and concrete, it's algebra, whereas the one you were translating from was a complicated and difficult sort of thing. Okay, now these transformations from one category to another, they can either keep the maps going the same way or they can reverse them. In the case of the fundamental group, it keeps them going the same way. So those are referred to as covariant as opposed to contravariant. Both kinds occur. Okay, so if we want to talk about classification, what we'll do is we'll assume that our collection of objects, the things we want to classify, forms a category. So there's a collection of objects and there are natural maps between them. And our labels will translate this category over into another one, preferably a simpler one. And well, we would, maybe it's just that the other category is better studied and easier to work in. We would actually like our labels to forget some things. The fundamental group forgets quite a lot. It can't tell a disk apart from a point. But it remembered enough to be able to answer to greatly simplify the question that we had with the Brouwer's fixed point theorem. One of the first examples that actually involved C-star algebras is something called the Gelfand representation, which associates to a commutative algebra a set called its spectrum. And the odd thing about the Gelfand transformation is that it forgets nothing. It's basically an identification of the two categories. So questions in one are exactly as difficult as questions in the other. And that wouldn't really count as a useful classification, except that one category had already been well studied. And just translating the questions over helped answer the ones in the other category. But we would like to be able to forget some things as well. Okay, so when we're talking about things that we would like to forget, what we want to do is identify kind of the maps that we would like to make trivial. We would like to be able to distinguish between the objects in the category that we're studying, but we would like to be able to say that certain symmetries that the object has with itself are not really important, so we want to forget about them. Now, an example where you want to do this is something called an inner automorphism of a ring. So if you have any kind of invertible element, you can just conjugate by it, multiply by the element and its inverse on the other side, and you quickly see that that's an automorphism of your ring. Now, if we think of the ring of matrices, then this is what gives you just a change of bases. Now, normally, if you're working with matrices describing linear transformations, a change of basis is not really a significant change. It's something you'd like to ignore. So this is an example that we would want to consider trivial if we were trying to classify something that involved matrices. So we would like to wipe out the inner automorphisms, say. And in this way, if we had a set of labels that ignored those, we would say that the information we were losing was no loss. Okay, so if you have this, okay, so I'm just going to switch screen here for a moment. Okay. So what's the situation we've got here? We have an original collection that we were going to be looking at. We have a category to be classified. We have a target category. And we have our labels. The label is usually referred to as an invariant. Okay, so what do we want? If we have two distinct things over here, we want them to still be distinct over here. Okay, so our invariant is, you would say, injective on the objects. But if we have certain maps from something to itself that are trivial, they just get sent to the identity. So our trivial symmetries. They just get sent to the identity map. Okay, and so this category over here is simpler than the one we started with. Okay, and so you can answer your questions over in the second category, like we answered the Brouwer fixed point theorem with we were able to answer it as a question about groups, whereas it was difficult as a question about the disk and other spaces. Okay, now once you've got your invariant and is able to do that, you've got the question of exactly what actually comes up. Okay, it may not be that everything out here actually occurs as the invariant of something over here. Okay. So what actually comes up? Right. And that question is goes along with the classification question, is referred to as the range of invariant problem. Okay. You're thinking of the map on objects as being like a function. You want to figure out what its range is. Okay, really to have a complete picture with your given classification, you need to solve both of these together. Okay, so now I'm going to get to some more concrete examples where this approach to classification was used. Start off by looking at an object that's maybe familiar to the people in the physics department, something called the car algebra, the fermion algebra. When studying certain kind of particles called fermions, you use things that are called annihilation and creation operators. And these satisfy certain relations called the canonical anti-commutation relations that derive from the physical properties that these particles are supposed to have. And if you actually look at the algebra that's generated by these annihilation and creation operators, you see that it has a fairly nice kind of mathematical structure. You can think of it as an increasing union of square matrix algebras, and then we see here is just the matrices of size 2n by 2n. Okay, and you can think of it as an increasing union of those where you include one into the next by putting it down the diagonal. Okay, and then the car algebra is just you allow yourself to take limits. Okay, and these objects come up in various areas in physics. Similar ones occur in some different kinds of models. But they're an example of what is known as an AF algebra. So this is Todd's third C-star algebra today. The first was MNC by itself. The next is continuous functions on a space. So if we think of these AF algebras, they're an increasing union, take a closure, and the algebras along the way are these direct sums of matrix algebras. Okay, so these things cropped up in various areas in physics, and in the 1970s, the question of classifying them all was closely looked at. There was the first classification of these things actually involved a rather complicated diagram, but then in the mid-70s, George Elliott managed to use a classification of the kind that we've described here. He had an invariant, which translated the question from the category of AF algebras and their natural homomorphisms over to a problem about groups. There were very particular groups. They're abelian. In other words, the operation is commutative, so you can think of it as a plus rather than as a multiplication. And they also have an order relation. So there's a less than or equals among the elements of the group. And so these K0 groups, what Elliott showed was that if you had two AF algebras and you had an isomorphism between the K0 groups, then it actually came from an isomorphism between the AF algebras. So the groups were the same, the algebras were the same. So you could label the algebras with their group, which was a much simpler object, and you could answer questions about the algebra by looking at the group. Well, in particular, you could say when two of them were the same, but it also included information about when one of them sits inside the other and so on. That's sort of the first big part of the picture. You have all the algebra, you have everything classified. The next question, of course, is the range of invariant problems. So what actually occurs as the ordered group of an AF algebra? So that problem was answered a few years later. It's known as the F-Ross-Handel-Duchenne theorem. Okay, now after that, with the success with AF algebras, Elliott launched a really ambitious program to try and apply these techniques to more and more operator algebras, so larger classes of operator algebras. And this turned into a whole program that lasted probably about 30 years, produced lots of work, and it has now more or less been completed. So there's a well-known and described class of these operator algebras, and a gadget called the Elliott invariant, which includes the K0 group and has a few more things added into it. And if the two invariants are the same, the algebras are the same, and we know what all the invariants that arise are. So we've kind of completely labeled this whole class of algebras. We can tell when one sits inside another and so forth. So since the completion of that program, the attention has, of course, turned to its applications. C-star algebras arrive in a lot of places because when you have some other kind of object, like say a dynamical system or something, there's often a C-star algebra associated with it that you can build out of it. And so now people are using the Elliott program to study other things by saying, okay, you take this other thing you want to study, you build the associated C-star algebra, compute the Elliott invariant, and the Elliott invariant tells you things about the C-star algebra, and then that tells you things about the object you were interested in. And the other way in which it's currently being extended is in taking a C-star algebra and then adding some more structure to it. So a C-star algebra would say a group action on it, or a C-star algebra with something called the real structure or a grading on it. So I'll just have a brief look into some of the things that are going on in that sort of area now. With the C-star algebras that I've mentioned and looked on so far, they're all algebras over the complex numbers. That's kind of the natural place to do most linear algebra. But you can also define C-star algebras over the reals, and these have a nice axiomatic description like the complex ones. You do have to throw in a few technical details that I won't go into here. And with these real C-star algebras, they have a complexification. Just like when you're working with real numbers, you can always throw in the complex ones on the side. If you have a real C-star algebra, you can form a larger one called its complexification. And you can kind of go back and forth. You can have a complex C-star algebra, and you can have an operation on it that's like complex conjugation. Just like when you're working in your complex analysis class, you have this Z goes to Z bar map. And then the reals are identified by the ones where Z equals Z bar. You can do something similar with a complex C-star algebra and distinguish a real part out from inside it. Now these things are of interest partly because of the physical models that involve them. So a type of material that's currently being used are something called topological insulators. One of the ways in which these are described is you have a Hamiltonian that describes them, and it's an insulator because it actually has a gap at zero in its spectrum. And you can then model these by looking at the algebra generated by all the possible translates of the Hamiltonians. So you get an algebra of observables. This is one of the ways that C-star algebras are used in physics, is that the observable quantities are modeled by elements of a C-star algebra. And then in these models, the different kinds of symmetries are described using extra structure that's built into the C-star algebra. So for example, some of the symmetries that these topological insulators, these materials have, one of them is called time reversal. That's, well, it's kind of clear what that is. If you have a dynamical system with a time variable, do the laws stay the same if you run time backwards? So that's one kind of symmetry that a system could have. Another one, if you have a crystal with an electron bouncing around between the different points in the crystal, there you've got a negative particle that's moving around from point to point. But you could also have the absence of a particle. So everybody is collectively one electron short, and you could think of that as a positive thing bouncing around from place to place. That kind of if that sort of symmetry leaves the laws unchanged, that's called particle hole symmetry or charge conjugation symmetry. And then there's something also called chiral symmetry, which is a symmetry that the spectrum, the energy spectrum of the Hamiltonian may have. And these things are described by either, well, they're described by symmetries of two kinds, whether they're what's called a real structure or a grating. And so this kind of leads to motivates what's currently going on with my own work is studying classification questions for these real C-star algebras with gratings or both. Okay. So I think I will stop here and ask instead for questions.
So, excuse me, in terms of questions, I guess you'll have to disconnect. If you just turn your mic off, just.
Oops. Yeah. So the question was, could you have two real C-star algebras with more than one complexification? That I think was the way you wrote it around. What you can have is you can have different real C-star algebras with the same complexification. So you could have a complex C-star algebra and two different real structures on it. So, for example, if we have M2 of C as a complex C-star algebra, that's the complexification of 2 by 2 real matrices, but M2 of C is also the complexification of the quaternions. So you can have a complex C-star algebra and two different real structures on it, and the real C-star algebras not being the same. Okay. So yeah, often because we're much more familiar with complex C-star algebras than with real ones, we usually like to think of the real C-star algebras as you have your complex C-star algebra, and then you have the real structure on it, which is the complex conjugation that gives you the real part as the part where things are equal to their conjugate. And then it turns out that you can have a nice complex C-star algebra, and it has conjugation operations on it that give you distinct real parts, not just moving them around, but they're actually not even the same. That's all. Okay, so same complex algebra. Can have different real forms. And some of the questions that have already been asked is where we have the complex algebras are in one of the classes. They're in one of the collections that has already been looked at by the Elliott program. We know them, we're happy with them. And then when you have one of them, can you describe all of the different possible real structures that that algebra can have? And it could turn out to be another classification problem, is classify all the real forms that a given algebra can have. On the other hand, your question going the other way, I don't think that's,
Yes, okay, but
I don't know.
If exactly completely opposite, you may have very unintuitive examples of same real structure with different complex structures, non-identical complex structure, even a continuum, and try to classify how many can you get there. And so this could be get as many as can. And the examples like this of real structures, real characters, that mean analytical set of complex structures.
Do you, so what do you require about the norms? I mean, do they?
Just, I mean, you to do the same thing. Yes. So lambda, norm of the lambda, x to this will absolutely lambda. That's on the right.
Okay, so I guess your question there is, can you extend when you can you extend when you take the algebraic complexification? You're asking, is the extension to a new norm?
Yeah. How many? Yes. How many? Complex algebra can be the same. Yeah.
Right. Well,
I don't know. I'm.
Well,
we're coming more from from Banach space.
One of the very nice things about C-star algebras as opposed to general Banach algebras is that for a C-star algebra, the norm is completely determined by the algebra structure. Whereas with a Banach space, you could do all kinds of funny things with the norm. So yeah, you might have more possible ways of putting a norm on the complexification. If you're not assuming it's a C-star algebra. With a C-star algebra, it's unique, so determined by the algebra.
Other question?
Okay.
Thank you, Andrew. We're working on
All right. So again, thank you, Dr. Dean, for your presentation this morning. Just a couple of reminders. It is on the exam. No, there still is a lot still going on in R&I week. So if you haven't looked at the schedule and planned your next couple of days, I would encourage you to attend a number of the upcoming events celebrating research here at Lakehead University and our 20th year of having an R&I week. But as Dr. Dean reminded me, 55 years or so of research at Lakehead University. The other thing I would like to remind you of is there are cookies and coffee. Make sure you grab one on your way out. I know that students run on cookies and free food. So again, thank you for attending this morning, and I wish you the best for the rest of the semester for the students. Take care.